It's a great honour and privilege to have been elected to the Academy of Science, so I thank everyone for that. I've been told that since I'm the first speaker after lunch, you want a nice simple talk, so that's what I'll do for you, I think. So I'm going to talk about digging. As you can see, there's some people here digging. Now, this is peat, so digging peat in the early 21st century is probably not a good idea. Digging up the soil, the organic soil of the world and burning it and putting it in the atmosphere, probably not a good idea. But this was an old photo and I like it, and so I thought I'd use it. A few gender issues here as well, I think. Look, I'm a soil scientist. Where did the title come from? Well, I stole the title. It's actually the title of the first poem in the first collected poetry of the Nobel laureate Seamus Heaney. And he talked about digging, and he lamented the fact that, unlike his father, he couldn't spend his life digging, so he had to, as he said, he had to dig with his pen, snug as a gun. But unlike Seamus Heaney, I've actually been allowed to dig all my life and all over the world. So that's what I'm talking about today, a story of digging around the world. And I just wanted to say, I'm thrilled about being elected here, not for me, but because I come from a very small discipline called soil science, which lots of people have never heard of. And when you try to find it, you know, it's in this is the universe of scientific disciplines, and it's hidden somewhere very deep in this little galaxy here. So one thing that did happen to us, though, was when the ERA came out, we got our own FOR code. So now people have actually heard of soil science. So ERA is good for one thing at least. Look, what about soil science? Who does soil science in the world? Well, obviously the usual suspects: USA, China, India. Here are the numbers of papers from various countries. And when you normalize them by citations and populations, you find that Australia does very well in the world. It's third or fourth, but New Zealand actually beats us. So it's New Zealand, Germany, France, and Australia in the soil science stakes. So I'm talking here for Australian soil science. Just want to say it's a small discipline, but we're good at it. We're good at it in Australia. We have about 1,000 soil scientists. There are about 60,000 soil scientists in the world. And it's really crucial for agricultural and environmental management. If we want to manage our landscapes sustainably, we need to understand our soil and its science. So let me tell you about my journey a little bit. So my digging journey started in 1976. Yes, 40 years ago I started this scientific journey. And it started right there, right at that point there. And this is a little transect across a rural part of the world. And I dug about 100 soil pits across there and looked at the soil. And what do we find? We find what we find in soils: horizons, various ages, how do they form, and large variation across the landscape. And here you can even see evidence of past climates. This is solifluction from the last periglacial period, these arcs that you see in this soil profile here. So that was the start of my journey, and if you want to know where that is, here's a bigger picture. This is the city of Aberdeen. I think Mr. Trump has a new golf course over here, and this is the transect. And just to put you in context, we're up in northeast Scotland in Aberdeenshire, and I come from southwest Scotland with Galloway. And we've only really had one famous scientist in all of time, I think. It's not me. Now, going from that transect up until 2016, now what we do is we make maps of the whole world. So this is our assessment of of global soil carbon, very important for climate change mitigation. And this is our mapping at, this is 500-meter resolution, soil carbon all over the world. So we've been able to scale up from that little transect to the whole world, and I think that's what my journey's really been about. So it's been a scientific journey. I worked on something called pedometrics, which is really, if you like, to think the statistics of soil and soil variation. A couple of applications of that, digital soil mapping, which we took to the world, and an application in precision agriculture, which relates to what John Kierkegaard was talking before lunchtime. I want to say a little thing about soil security and proximal soil sensing. In terms of soil variation, what we see is that soil is variable at certain scales, more variable than other environmental objects. And I think at these scales, soil actually controls the ecosystem. And we can see certain scales there that soil is very important. If we look at the diversity of soil across continents, we'll see that Australia or Australasia is less diverse than other continents in terms of its soil cover, largely to do with the fact that it's a very old continent and the soils have become more uniform over time, whereas South and Central America are very diverse. Part of pedometrics is trying to model how soil forms. So there is a theory, we try to generate a theory of soil evolution, soil landscape genesis modeling, so that we can find out how long it takes soil to evolve, how do these different horizons evolve over time. And it's a combination of fast processes of erosion and deposition across the surface of the land and slow processes of weathering and translocations within the soil profile. We do that on landscapes. We evidence that using cosmogenic radionuclides and thermoluminescence, and we can model this process. This soil here in this part of New South Wales is 80,000 years old, an order of magnitude older than the soils that you see in Northern Europe or in Northern America. That's part of the reason why we have to look after our soils. Our agriculture has to be a bit different. Applications include digital soil mapping and precision agriculture. Why digital soil mapping? Because conventional soil maps that we've made for 100 years really are not quantitative. They're just qualitative, colored pictures, if you like. And so now we need to move to a quantitative phase. And we've done that in a project called Global Soil Map, which tries to give us a 90-meter spatial resolution soil map with uncertainty for the whole world. The application on that in Australia is the Soil and Landscape Grid of Australia, which was done as part of the TERN activities, and a big collaboration there with a number of organizations. This is Tasmania. This has got a resolution of 3 arc seconds or 80 meters, but you can see that there are large parts of Tasmania where the subsoil pH would suggest that there are areas where you wouldn't want to grow crops and so on. And we can use this digital data to look at new enterprises for Tasmania. It's actually getting warmer, so there's more potential, and we use all that data to show where there are areas of very high versatility for new cropping. We've also applied our algorithms we developed in the US, running it through the hypercomputers to produce new data for the US, the whole conterminous United States. And that's used, an application of that is to put that in the NOAA land surface modeling, but at higher resolution than normally done using higher resolution soil data, because we soil scientists think that that's missing from our soil. It's missing from the modeling work that's done. When we look at individual fields, we see that when we look at yields of crops, there's often a threefold variation. It can vary between 1 and 3 tons, or a fourfold variation. That's common in every single field that you look at least in Australia. And the cause of that, when we investigate that, is soil variation. So soil variation at the scales of hundreds of meters causes 3 or 4-fold variation in crop yields, which is not really captured yet in our crop growth model. So there's a bit of work to be done there. And of course, that variation is systematic. We can understand it. We can map it. Once we can map it, we can use precision management, digital agriculture. We can use technologies to apply different rates of nutrients, different rates of herbicides across these fields and optimize production. There are many global existential challenges, things that if we don't get them right, we will lose the planet eventually. We all know about food security and water security and climate change. I would contend that soil security is equally important existential challenge for the world. To understand it, it's obviously multidisciplinary. It's got biophysical dimensions, but it also has economic, social, and policy dimensions. And I'm working hard at the moment to try to quantify all these dimensions to secure our soil. And these are a couple of different situations that we should look at. Finally, getting back to the spade, we don't actually use a spade. We use all kinds of new technological devices to study soil, from the gamma radiometric to near-infrared and mid-infrared, UV visible light, and radar to look at soil. So that's how we do it these days. So thank you very much.
Thank you, Alex. Any questions? Yes, one over there. Microphone over here, please.
Sorry, this might be a simple question, but you showed that map of Tasmania and you showed the pH level. Obviously, that comes from a satellite data, no? And so that kind of resolution you achieve, I just wondered how you get the type of resolution of the pH of the soil.
It's a combination. Obviously, we use satellite and all different kinds of imagery and data, but the main data comes from point observations of soil, and we combine the two together to produce that kind of,
Is that largely farmers?
I would call it a map, yeah. And we produce the estimates at different depths in the soil and also the uncertainty of those estimates so we can do risk-based management and modeling.
Thank you.
Professor Cohen?
What actually determines the age of soil? Is it to do with the microorganisms in the soil, the number and type of worms, or what is it?
Well, I think what I mean by the age of soil is how long has it been since weathering began? So you imagine that this fresh or relatively fresh rock at the soil surface, how long does it take for that process of weathering, which is done chemically, physically, and biologically, to act on the soil, transform the minerals, create new minerals, organize itself. So it's a process of transformation and organization. And what I'm saying is these profiles that we're looking at in New South Wales were of the order of 70,000 years. If we were looking at a soil profile in Scotland, it might be of the order of 8,000 years or 10,000 years. Yes. Okay.
Okay, thank you, Alex.
The famous, I thought I put a question in. The famous scientist was James Clerk Maxwell.
Thank you, Alex.